Hello everyone, I am Enrique Mas-Candela and I'm presenting the work I did with María Alfaro-Contreras with title Sequential Next Symbol Prediction with Optical Music Recognition. As most of you may know, optical music recognition is the task that the computers do for reading music notation from documents. So given an image of music, an algorithm decodes it into a digital representation. Like you can see in the example, given the image of the score, it's decoded into a simple readable representation that can be read in a computer. Well, one of the existing state-of-art approaches for end-to-end optical music recognition is the CNN-CTC, which consists in a convolutional recurrence neural network trained with the CTC loss. This model, given an image, can be trained to decode a sequence of symbols just by knowing that sequence. This approach has been demonstrated to perform very well in reading music notation, but however, it usually needs big training sets to be trained properly. This can be a very big drawback when transcribing music. Old music manuscripts, that is very common that they consist of very few pages. So the training process would be very difficult in that case. For trying to solve this, we present a new approach which tries to solve the task in a more simpler way, which is inspired by human reading behavior. Our approach is a two-step process, which consists of the next symbol prediction module, which in each step predicts which is the next symbol that is going to be read in order to read the reading order of the score, and another module that predicts the shape and height of that note. Here you can see an example. The next symbol prediction would predict the location of the next symbol, and the other module would predict the shape and the position. An overview of the approach would be this one. So given an image, in each step, we would predict where is the next symbol by the NSP module, and we would predict the height and shape of that current symbol, giving as a result the sequence of symbols and with its shapes. Okay, so giving some details about the approach, about the next prediction module, it's a convolutional neural network that predicts a regression of two coordinates, x and y, which has an output of the spatial differentiable spatial to numerical transform, the DSNT activation, which has been demonstrated to perform well in location regression tasks. And we trained it with a BDG16 network with inputs of 192 per 192. About the shape and height module, it consists of two classifiers. Each of those has to predict each one of the tasks. By one hand, the location of the shape of the symbol, and on the other one, the position of the symbol, the height in the score. It has independent outputs, as I said, and as the backbone of the architecture, they are a similar architecture to LENET 5, which has inputs of 200 by 200 for the shape and 250 and 125 for the position. The experimentation we did was with the captain corpus, which has the characteristics that you can see here. We performed a 5-fold cross-validation for training, separating in 60% for training and 20% for validation and test. We use this corpus because it's very common and in optical music recognition, and there are some experiments published with those corpus. This corpus consists of a set of stuffs which 53 different shape classes and 16 different positions. And the annotation includes the bounding box of each symbol, which we used its center for detecting the location of each symbol. And you can see here an example of an image of that corpus. The results we took in the experiments, for evaluating them, we used the categorical classification accuracy, which is basically the success rates. We use this metric for evaluating the classifiers, both the shape and height. On the other hand, we use the continuous Euclidean error rate for the evaluating the error on the next symbol prediction module. This metric measures the error of a prediction being predicted for the previous predicted position. And on the other hand, we use the symbol error rate for evaluating the full sequence. That is the well-known normalized edit distance, which we assume each pair of the shape and position as a single token. Well, I didn't mention, but here you have the results. You can see that the level, both classifiers seems to work very well. Results near the 19%, and the next symbol prediction module has a approximate error of 16%. We did an evaluation of those models, training them with different amounts of data to show how it works with different amounts, and we compared it with the baseline. The baseline we use for this is the CRN-CTC approach. In this graphic, we can see how the training performs given a certain amount of steps, and you can see there in the red line that with a little amount of steps, our approach performs better than the actual baseline. But however, with more amount of data, the CRN-CTC performs a bit better than our approach. Here you can see an example image of the predictions of the next symbol prediction module. The red dots would be the predicted dot paths or a next symbol prediction module, and the green crosses are the ground truth. You can see that in most of predictions there are a slight error, but this error is not affecting too much the prediction of the classifiers of the height and shape. It can be due to a training with data augmentation to trying to solve this problem. Doing an analysis of these errors, we inspected the SER, the symbol error rate, and we found that 6.5% of the error that caused the SER were due to insertions, and 14.5% due to deletions, respectively. So more or less 20% of the error given by the SER is due to the next symbol prediction module, and nearly 80% of the errors were substitutions that were errors done by both classifiers. We also see that the take-all window for the classification entails a glass ceiling. It didn't allow to perform better results, and we also deduced that an imperfect symbol location is not that relevant for predicting the next one. So an error in the next symbol prediction module doesn't need to be an error for the next one. So it can fix its own errors on the way and finish the stuff correctly. In fact, it can affect the classification, but as I said before, we used some augmentation procedures for simulating these issues. And well, thank you, everyone. That's the presentation. As if anyone has some questions.
Thank you very much. Also for keeping the time limit. That's spot on time. And I've already seen a raised hand. No, I thought I saw, yes, now I see a raised hand. Alicia, please.
No, Pedro was first.
Oh.
No, I was just applauding. But anyway, I can make a question. Because as I understood you, your next symbol prediction model predicts the center of the bounding box?
Well, in fact, it predicts the center of the next symbol.
So there is no prediction of the size of the bounding box at all? Sorry? Is there no prediction of the size of the bounding box?
No, it just predicts the center of the next symbol. We did an experimentation predicting the full bounding box. We in fact did predict two locations: the top left location of the bounding box of the symbol and the bottom right. But the results that we got were not as good as those ones. We suppose it's because in the window that we were using, we tried to be as small as possible to simplify the process. The center of the symbol was always present in that window, but sometimes the bottom left corner weren't present on the window.
Okay. Thanks.
Now, Alicia.
Yep. Thank you for the presentation. It's curious to see that you go towards the next element to look at, and this reminds me the attention that Alex was explaining in the morning concerning the different digits in the score. And then the question is how far we can go with this. So could we tackle polyphonic scores? Can we even link this to the eye tracker that we were discussing before? Because in the end, if we are following what the musician is reading, I understand that when you are reading a chord, well, you are reading the chord, but your eyes go to the different, or at least a rough space in the chord. So somehow this sequential next symbol prediction is a kind of reading order prediction or eye tracker prediction. And this could be applied to polyphonic scores, right? So do you have any thoughts on this?
Yes, we have not done any experimentation on this, but one of the benefits that we think that has this module is that can predict the next symbol or symbols that are going to be read. So we think it's totally comparable with polyphonic scores. I mean, if you are in the current symbol, when you look to the next one, you can see that there are more than one and predict more than one center, and could be in that way comparable with polyphonic scores.
And in this case, even trained with eye trackers.
I think so.
I hope that answered your question, Hiro.
Yeah, thank you.
Can I ask?
Yes, please, go ahead.
So following up on that question, I'm wondering if you can actually learn harmonic sequences, if you think you can predict position of next chord, is it really learning? I mean, it'd be great if it's learning like harmonic sequences in the end. What do you think?
What do you mean actually by the question?
Okay, so when you're doing what you're doing, the monophonic sequence, you're basically learning, it must be basically learning how a melody looks, right?
Yeah.
So it won't jump up a ninth or, you know. But you said you can there's a possibility of learning next chord. So I'm wondering if you're learning sort of the rules of melody or potential melodic lines. When you say you can learn chords, is it possible that it could learn harmonic sequences? I'm sort of abstracting upwards here, and it's actually kind of a neat idea.
Yeah, I think it should be possible, but we haven't thought about that. Actually, we only changed the model with monophonic scores. So the approach we took only predicts actually the next symbol and predicts which is that symbol. But actually, I think it could be able to predict directly the chords by one hand, and the other one, it can be trained with several paths of reading and predict different next symbols and different locations of that chord, and individually give a prediction of the notes of the chord.
Great, thank you. Inspiring.
Could I say something?
Very quick.
Yeah.
Alex? Oh, yeah, very quick. I think that according to the question by Ichiro, I think there's a misunderstanding here, is that the predictor doesn't predict the pitch or what is going to find, but according to the pixels, it predicts where is it. I mean, it's not predicting if which is the note that is going to be next, but where is it? Just according to the pixels. So there is no a model of melody.
Well, I mean, I don't know. If it's visual, if you can tell where the position is, yes, I am abstracting up, right? But if you know the positions, that'll eventually get to melody, right? How melody behaves, that it doesn't do lots of jumping up and down. That's what it's sort of learning. And it's basically learning what melody, or at least this type of melody, behaves. So if you keep going, it may be possible to learn chord sequences.
I just wanted to say that it's not predicting where which is the next note. There's no one melody language model of the melody, but just according to the pixels that are white or black is predicting the position.
I understand, but I don't know where there's real difference.